All right, cool. So yeah, thanks so much, Lee, for inviting me. My name is Andrew Morris, and I work for the Ethereum Foundation. Been there for about 4 years now. But I'm
which team are you from?
Which
team?
Oh, within the Ethereum Foundation. So they have a sort of a branch called PSE, which now stands for Privacy Stewards of Ethereum.
Very new, right?
Yeah, well, yes and no. The name Privacy Stewards of Ethereum is new, but we used to be called Privacy Scaling and Explorations.
Oh.
So it's still PSE. It's kind of still the same people that have been around for a few more years than that, but we like rebranded recently. So yeah, I have kind of changed what I've been doing a few times within the Ethereum Foundation, and this project is actually not super active anymore. Like it is still an Ethereum Foundation project, and if people come to me and they want to use it, then I can still help people and like on company time. But it is a bit limited, so yeah, slightly disappointed about that actually, as you might see. So it would be great if somehow we could revive this project, breathe new life into it, because I think it's pretty cool. But yeah, thanks again for inviting me. I think I mentioned that, and yeah, let's get started. Oops. There we go. Okay, so what is MPC? So this might be interesting. A quick show of hands. Do you guys know what MPC is? Not to be confused with MCP, which is the AI thing.
I guess people here know MPC more than MCP.
So yeah, so a few people are kind of familiar with MPC.
Most of us are.
Yeah.
Okay, cool. So conceptual stuff. I think you might still enjoy this story. So MPC stands for multi-party computation. And I have this little scenario to help kind of explain the idea. It's probably useful for some remote people that are recording. So when was the last time you were in a situation like this? You know, probably never, right? Hopefully this makes you a little bit uncomfortable. That's kind of the point. The point is there's a taboo about money, and it exists for a reason. But MPC this is one of the kind of scenarios that MPC can help us with, because MPC is a privacy preserving technology, and it can enable kind of new forms of communication that kind of aren't really possible otherwise, unless you trust somebody in the middle with that sensitive information. But if it's like really sensitive information, it's like, who are you going to trust in the middle, right? So yeah, your conversations might look something more like this. Even you might be thinking about things that are more consequential to you, but taboos exist for a reason, so you might find yourself talking about way a little more than you like. So to think about what you're missing out on, if you could see all of the money, that would be a superpower, right? Like, should you go somewhere else? Do you have it pretty good where you are? Is your friend making more than you for doing the same or less work? You don't know these things, but if you did, well, usually you don't know these things, but if you did know them, then it would be extremely useful information. But it's too bad that crystal balls don't exist. So what are we supposed to do? Remember, there is this taboo problem. And so quick word of advice on the side, it's like these taboos, sometimes they should be broken. There's enormous value, and so if you feel like you're in this situation, maybe consider breaking the taboo, but there is another solution. So if you think about it, this is I need to remember to slow down. I see that it's just on my screen. If you think about it, this is a mathematical problem, very counterintuitive, because it's strange to even ask this question, because we don't actually need to know exactly what somebody else makes. We just want to know what is the kind of like 1 or 2 bits worth of information that would actually help us just make a decision in the real world. And so I would suggest in this situation, if you're just sort of like comparing with a colleague or something like that, you would like to know, are you in the same ballpark as each other or not? Or if not, who is above and who is below? And so you'd be much more willing to kind of share that information in that scenario, because it takes very little information. You're not going to get in a very awkward position where there's a very big imbalance. But if you are different, you'll find out that you are significantly different, and maybe you could do something about that. So yeah, MPC to the rescue is my suggestion. So this is exactly the kind of problem that we can solve in general with MPC. It doesn't have to be a simple comparison. In theory, we can compute literally anything that we like. So MPC is a cryptographic protocol that allows us to get inputs from different people that do not trust each other. And somehow we're able to do a computation over those inputs and have only the output is revealed. And we're also able to get sort of cryptographic assurance that that calculation is correct as well. It's not just correct if people do the right thing. It is, you will know that it's either correct or, if somebody violates or abandons the protocol, obviously you're not going to get the answer. But if you do get an answer, you will also have cryptographic assurance that it is correct. Cool. So for this specific example, I created this app called Ballpark. It's very simple, works on your phone, just in the web browser. Go start, and one person press post, and then you get to choose what about the same means. So you can configure, I suggest 15%, but curious what people think. The other person selects join, scans the QR code, then you can input your numbers, and then you calculate, and you just get an answer that looks like this.
So what's the 15%? What's that for? Based on 15%.
Yeah, so we're going to get like 3 different outcomes from this calculation. You're either going to be higher or lower, or about the same. And so 15% defines what the about the same threshold means. So if the higher person is 15% greater than the lower person, then it will be exactly on that boundary. That way, if you find out that it's more, you know it's more than just like 0.5% more, which would not be very useful information. Cool. Yeah. And so, yeah, as I was mentioning before, there is no trusted server in the middle. We're doing this with math, not with trust. And so there's a cryptographic thing that achieves this. There's an end-to-end encrypted tunnel between the 2 phones as well. So there is no possibility of seeing anything in the middle.
Why end-to-end? Because you saw QR code, right?
Yes, the QR code contains an encryption key. Specifically in this implementation, you hash the encryption key, and that gives you a common ID that you're able to find each other on a peer-to-peer networking thing. And then you use the encryption key to actually encrypt the communications so that there's no spying in the middle. You know that you must be talking to only the other person who saw that QR code. Yeah. Cool. So back in our story, we might get an outcome that looks like this. So you can sort of focus on the kind of practical information rather than, hopefully, than sort of getting distracted by the emotions that might happen. Cool. So if you want to try this out, this is a real app. So you can scan that if you'd like, or there'll be other links that you can find it later if you're interested as well. I'll give you a second.
Does it require internet connection or like peer-to-peer network?
It does require an internet connection in this version. Yeah, it actually uses WebRTC, and there's a public signaling server that it relies on. But yeah, you could, in theory, do it obviously without the internet. But this implementation does. Cool. All right, move on. Okay, so part 2 of this talk, there is this tool called Summon as part of the project, which is a language that I created. It's very much like TypeScript, and because you might wonder, right? I said you can do any calculation inside of MPC. So the question is, how do we specify that calculation? And the problem that we have, I think I actually have a slide describing this. Yeah. The problem that we have is, in order to apply this MPC technology, at least the version of the MPC technology that I'm talking about today, we need to specify this calculation as a Boolean circuit. And so, so you have this challenge potentially. It's like, oh, I want to do this interesting calculation, but somehow I need to come up with a Boolean circuit to represent that. So Summon is our solution to that problem. And so the language of Summon is not exactly TypeScript, but it uses the same syntax, and kind of on the surface it's very much the same language. And so if you've written sort of JavaScript, TypeScript before, most of that muscle memory should apply, and you should be able to be very productive in Summon very quickly. Cool. So for example, just wait for that to update. Yeah. In our Ballpark app, when you specify this 15%, that goes into a line like this, where you ask for a public input, and then when you input those things, these are kind of like ordinary private inputs. And so you can get them like that. And we're going to output a result. And keep forgetting that this is behind. Yeah, it's updated on my video is frozen as well.
You might just stop the video so the bandwidth saved.
Yeah, that might help. Okay. I can maybe switch to the Wi-Fi here.
Tricky.
Tricky? Okay,
You
maybe
need my
not.
password. No, it's something.
That's all right. Let's.
We can hotspot.
Maybe you can
I have my hotspot, but I just thought the if being on the
Maybe
same
you can turn
network might
turn off your own
Turn
video.
off your own.
Yeah.
So
That one, right?
So you could also try the Uni-Sydney guest Wi-Fi.
You need to register.
You need to register and have the authorization, which can be done in 2 minutes.
Okay. Well, we'll see whether this improves things. Cool. So we can implement this compare function separately and just declare that as our output, and then we're just sort of writing sort of plain code to make this work. Let me skip over some of the details in here because we have a lot to cover. So this is kind of the key line of the computation. So because we want to know whether it's significant or not. Otherwise, just doing a comparison is relatively straightforward. But measuring that 15% is interesting because in particular in Summon, we only have integer arithmetic. We don't have floats. It's just not kind of implemented. It's possible to do it, but hasn't been done. But yeah, you can get away with integer fairly easily for most use cases. So yeah, it just represents this kind of thing. So we can do a relatively simple integer calculation to represent this 15% or whatever percentage you'd like to do. Cool, and then it's just a matter of saying, if this, then that, and to sort of recap a little bit, I think like the really kind of magical, wonderful thing about MPC is that you can think of this like code, when it's running on your computer, it's like, obviously, well, we live in the age where we can just sort of assume that we have CPUs and stuff. That's pretty magical too, right? But, the calculation really happens somewhere. Whereas in MPC, somehow we're doing this calculation, like we can literally say, if this, then that, and like that is the calculation that happens, but nobody gets to see that. There can be like internal computations, like up on this line up here, you can see this kind of conditional, it had to switch between this or that. That's a kind of branch that needed to happen. And yet, if we calculate later that the difference is not significant, this switch never gets revealed. And that's really important, and it is a property that does occur. It really is only the thing that gets output is the thing that you can recover. So yeah. So a little bit about implementation. So Summon works from within TypeScript as well. So you can do end-to-end TypeScript development to do MPC framework applications. And it looks a bit like this. These are just kind of the internal details, but you just kind of like pass it to the next part of the API. And yeah, I can go through this a little bit. So use this tool called Speedy Web Compiler to get a syntax tree out of that. And then there's a compiler which goes through this whole tool chain in order to do this so that we get some bytecode and we can run this in a virtual machine in order to build the circuit. We're not inside of the MPC protocol yet, by the way. We're just we're trying to get to this Boolean circuit that we want in order to then do the MPC protocol. And yeah, Summon is a fork of this TypeScript thing, by the way, which is a thing that I did outside the Ethereum Foundation. So Summon is mostly value script, which is a kind of a more ordinary programming language, but I was able to fork it to do this Boolean circuit generation. And so there's a lot more to talk about value script, but I won't go further into it unless you guys are interested. And so then we can generate this expression tree to represent any of these like things that we want to do. So there's a kind of evaluation of that that's kind of like a normal CPU where it doing like instruction by instruction. It also does things like this with the substitutions. So remember this like tolerance is this 15% number. And so rather than like actually keeping this part of the tree, the compiler can substitute the actual value for that one because that one's a public input. We don't need to do it inside of the MPC cryptography, we can just simplify the circuit instead. So we can add those two things together and we can just say, oh, we know this is exactly 115, and then we can eliminate that part of the tree and we just have 115 there. Cool, so then we just do these instructions and we can build this tree, we can eliminate those nodes in between. Feel free, I'm trying to like cover some of this fast, by the way, so feel free to stop me if you like, I don't mind questions in between.
Just a very quick question. So who's gonna run this compiler to get the security, the host or basically the question is, how about the other people know actually the host is indeed inputting the right circuit? Say maybe we were originally trying just to do comparison, but maybe the host can compile a circuit which is doing much more.
Absolutely, yeah. So if only one participant was just doing the circuit and then just saying, hey, we're doing this circuit, then you wouldn't have assurance that you're actually doing the calculation you're supposed to be doing, right? So yeah, the solution to that is, in this version, is all of the participants will independently compile the same circuit so that they know that they're all running the correct program. Yeah. And so yeah, it's important. I actually had some bugs earlier on in the project where the compiler wasn't 100% reproducible. And so I would get errors where, because they were trying to run different circuits and they didn't agree with each other. So I had to fix those bugs. You need to get exactly the same Boolean circuit so that we can simplify this way. So one thing that you might expect as well, by the way, like when you compile your application, that this circuit might be sort of like hard-coded into that source code. So that's one way you could do it. You might consider doing that for like really complicated circuits. But for these applications, you generally just have the compilations just done on the fly, especially because the circuit generation tends to be a lot cheaper than running the MPC protocol itself, which means that you might as well just do it on the fly, and it makes the development process a lot easier because you can bundle the summon source code into your application instead of just saying, hey, here's a bunch of bytes, just, trust me, bro. Which is, thinking a lot of applications. Cool. Anyway, so this is just simplifying the tree. There are these internal nodes, and we generally write flowcharts kind of like this. And so yeah, that's how that sort of thing works. Where are we? Cool. And so, but you might notice this is like multiplication and greater than, which is an arithmetic circuit. It's not a Boolean circuit. So
sorry, one more question. So actually a follow-up of the previous question. So when you do the compiler, it's actually everyone needs to write a small piece of scripting, or you write your own script for the functionality, then run the compiler to get the circuit, right? Say
kind of, yeah.
So say you write something. Let's say again we do same functionality, but using completely different, functionally they're equivalent, but the code are very different. Say square, I plus, right? I do plus then minus again, but the same functionality. But this get the same circuit out?
No. Not necessarily. Like you might be lucky and you might happen to get the same circuit, but generally not. Yeah.
But then how can we ensure the host and the participant exactly get the same circuit to compare?
Oh, got you. There is a checking step where we calculate the hash of the circuit and the entire configuration of this is the MPC protocol and all of the details that we intend to run against each other. And if those hashes don't match, it says nope. Not proceed.
That's exactly the confusing part. I just don't see how you can ensure when the input functionality is written in different ways, you can always get the same circuit out.
Why is it written in different ways?
Just like you write, we do equality check, right? I'm just doing like plus 100, then minus 100, then do equality check. Functionality is exactly the same.
Right, yeah.
But the circuit might be different.
Correct, yeah. So generally you need to run the same source code on both clients.
Oh, even the source code? No, not the source code. The circuit, the functionality we are going to run, that part have another piece of source code from somewhere. It's not written by the participant themselves.
Oh yeah, so generally when you do this, you will be running the same application with the same source code rather than having people independently write code so that then they can communicate with each other.
Oh, someone still provides the source code and you're gonna use the same copy.
Yeah, exactly.
So the constraint is on exactly same source code, and the hope is they compile to the same circuit. Exactly the same circuit.
Yeah.
Okay.
Yeah. I mean, it's, it should work. The compiler is pretty reproducible now. There could always be bugs, but like I haven't run into that for a long time now.
I wanted to ask like why the bugs in compiler would lead to not reproducibility. Like, is that like undefined behavior?
It was no, it was just a little so the version of that I ran into was only kind of a little technical input output of how the circuit was specified. So when you have a dictionary of like key value inside of there, right? Sometimes the dictionary can enumerate in a different order. So it didn't change like logically the functionality that was being computed, but it just kind of meant that the wires that were allocated, they were allocated in different places.
So dictionaries and order, like there's no ordering guarantee, so it has some fluctuation.
By default, yeah, it's because it's written in Rust, and by default, you use a hash map, and the hash Rust in their infinite wisdom, and I think it's kind of a good feature actually. They actually deliberately make it so that it enumerates in different orders on different runs, or I forget exactly how they key it, but just so that, because they're trying to tell you like, if you need reliable ordering, don't use a hash map. Yeah. Fun fact, by the way, if you want like to get the same circuit out of like different source code, like the different source code implements the same thing, and you want that when that happens to get the same circuit, it's in the kind of general version of that problem, it's actually impossible. There's a corollary between that and the halting problem. So you actually can't do that even if you want to allow people to write the same functionality in a different way. Cool. All right, let's move on. Right, so there's a boolefication step. So we have this arithmetic circuit with lots of interesting operations in it. Instead, we actually need literally like and XOR and not. And you have a complete system of logic. So we don't have OR gates, we have and XOR and not. And so yeah, boolify will take this and produce a Boolean circuit. So this section is quite large actually. So I'm gonna go through it kind of quickly. So what you do is, so when we're doing this boolefication, one of the interesting things is like when you have a constant, like multiplied by a constant, it's much, much simpler and faster. When you're running kind of like our code that we generally write, very general purpose CPUs, they just want to multiply two numbers together. It doesn't really matter that much if one of them is a fixed constant. Not necessarily, there might be optimizations that occur, but you might just have the normal multiplication operation. But one of the nice things about making a Boolean circuit is that you can actually take advantage of these like bits that are like exactly 1 or exactly 0, and produce a much smaller circuit than one that would have to deal with all the different inputs. So in this case, we're multiplying large by 100, and so we convert that into bits. And for the sake of example, I'll just do like a few bits instead of 8. And then you kind of imagine like going back to primary school and doing the kind of, the algorithm that we all loved learning, right? But yeah, it's pretty much the same thing, so I won't labor this point unless people want to ask questions, but the compiler literally does this type of thing inside of it. And so yeah, we get our partial sums, and then we do our sums. We can eliminate that one for the zeros, and those are zeros, and that one's 0. And this one is W2 plus 0, so it's just W2. W2 stands for wire 2, by the way, so it's literally a wire in our Boolean circuit. And so, but then we get to the interesting part, which is we want to like add two wires together. We don't know what they are. And so the compiler will insert new circuitry to deal with this. So we create this new wire 3, which is defined as the XOR of wire 1 and wire 2, and insert that there. And we also need to calculate our carry bit. So in this case, it's just the end of wire 1 and wire 2. So we declare that as wire 4. We can insert that one there. And then on the next step, because we have 3 bits we're adding together, the circuitry is a bit more complicated, but it's the same kind of idea, right? And yeah, so we do that one. And then this carry bit is even more complicated, but it's not too bad. And I think there are some wires that are being reused as well, but that's kind of like the full version. And yeah, and we just kind of finish this process. We get something that looks like this with all of the sort of circuitry that I had up before that defines these like derivative wires. And so yeah, overall we can go from this kind of thing to a circuit that looks like that. And that was the 3-bit version, by the way. So the like 16-bit or 48-bit or whatever version you do will be like more of a mess than that. So yeah, we actually represent it like this, and yeah, the protocol can deal with it in that format. Cool. So that's where we covered. So what MPC is, the summon language, generating arithmetic circuits, compiling those down into Boolean circuits. And so now we have this convenient way of getting the Boolean circuits that we need to do something interesting and plug that into an MPC protocol. And so now is maybe the more interesting academic bit for cryptographers, which is talking about like how does the MPC actually work underneath all of this, which is yeah this part of the diagram. Cool. So I'm going to talk about a kind of vanilla MPC protocol, which is just kind of like plain garbled circuits. Is anybody here familiar with the details of garbled circuits? Yeah, few people. Okay, cool. So you might notice that I'm not going to cover, this is a semi-honest protocol that I'm going to cover. So I will mention that later. The MPC framework actually implements authenticated garbling, which has another layer of complexity on top of this, but it's still based on this foundation. And this foundation, I think, will do a very good job, I think, of explaining if you have this, well, I think it's a good thing to think of MPC as magic. I think it is like a wonderful thing that happens, but sort of answering that question, like how is this voodoo possible, right? It does a pretty good job of explaining that. And then if you want to learn authenticated garbling later, this is actually the foundation that it builds on top of. Cool. So if we think about, we want to do computation, all computation can be boiled down to Boolean gates, as we've been talking about. And so for the sake of simplicity, we can think about a single AND gate. How could we calculate this AND gate? And for the moment, forget about like the higher order purpose of doing MPC between distrusting parties. Just think about like somehow this protocol achieves the fact that we're doing a computation even though we can't see the thing that we're computing. So for a sort of interim goal is like imagine that I want you to calculate something for me, but I don't want you to see what it is that you're calculating, but somehow I'm going to outsource the computation to you. So if we take the simplest case of that and think about an AND gate, how could you calculate an AND gate on my behalf without knowing what it is? Cool. So to make it painfully obvious what I mean by an AND gate, if we have a 0 and a 1 coming in, we'll have a 0 coming out, because an AND gate would be 1 only if the 2 input bits are 1. Cool. So these, you can represent AND gate using a truth table, which is the thing on the left. And so what we're going to do is we're going to do a transform over that so that we have this version of the AND gate on the right. And so the nice thing about that is that we can just kind of allocate whatever sort of random numbers that we would like to represent 0 and 1 and have this table. And so if you're able to look that up in the table for me, then you might sort of, that's a piece of the puzzle to not know what's going on. But you are still calculating an AND at the end of the day if you can calculate this. And to make it a little bit more clear, like these are literally like numbers in here. There would be actually like 40-digit numbers to make it secure, but for the sake of demonstration, you can think about 2-digit numbers. And imagine that you can't count to 100. Yeah, so does that make sense to everybody? If we can evaluate the logic table on the right, then that's equivalent to evaluating the logic table. Cool. Okay, so I'm outsourcing computation to you, right? So I am what's called the garbler in this scenario, and you are what's called the evaluator. And so I have this sort of grayed out. This is something that I know, but that you don't know. right? So I'm going to give you the information that you need in order to evaluate this AND gate on my behalf. So I'm going to provide you A equals 67, B equals 36. So you can see those things. And the question is, how are you going to evaluate and get this answer of 80 without sort of knowing what's going on? And so to achieve that, I'm going to provide you with some encrypted values. And this is the core idea, by the way, like that makes all of this work. So I'm just going to encrypt the correct answer using the keys that are needed as like the inputs that you have are the keys that you need in order to decrypt that answer. So you can only decrypt, you don't have the key to, you don't have both keys to any of the other things that I've encrypted. So you'll only be able to encrypt the value that you're supposed to have. And because these are arbitrary random numbers that like I've decided this represents 0, this represents 1, when you get the 80 out of it, you won't know what the 80 means, but I will know what the 80 means. So remember, you don't get the syntax, you just get these kind of random looking numbers. And so you can calculate, this is the key that you're going to use, you just join them together, and then you just try decrypting each of these. There's an optimization so that you don't have to actually do it, but in principle, to understand the underlying idea, you can think about just decrypting all of them. And so when you do that, again, you just get like numbers out of that. So you can tell these ones are incorrect because of the leading digits. And when you have the wrong key, use it with symmetric encryption, you just get like pseudo-random numbers out, which means that these leading zeros, they are like overwhelmingly unlikely to occur for the wrong entry. Because that's one of the reasons why we need 40 digits and not just 2, right? Otherwise you would have a 1 in 100 chance, but instead we have 1 in 10 to the power 40 chance. It's actually like 2 to the 128, by the way, but I just 40 is, if you're thinking in decimal, it's about 40 digits. Cool, so then you can say, hey, the answer is 80. Oh, but one little thing, you might notice that this is the like second row that you are successfully able to decrypt. Which is a problem because then you can say, oh, well, the second row means A equals 0, B equals 1, C equals 0, which would be terrible. But there's a very simple solution to that problem, which is that I will actually shuffle these numbers before giving them to you. And so now you'll still like successfully decrypt only this row, but now the fact that it was row number 4 is meaningless to you. And so you got the number 80 out, but you don't know what 80 is. And cool, so yeah, this is kind of one way to represent this idea. So this is a garbled AND gate. And so yeah, me as the garbler, I choose what all of these arbitrary constants are, just like at random. When you do the authenticated version later, which I don't have time to cover, one of the things we do is we don't just be random about these things, but the easy version can just do random numbers. And yeah, so oh yeah, sorry, the first thing I was gonna mention is that, so we did all this for an AND gate, right? But if you want some other type of logic gate, all you do is like encrypt slightly different values. So if I encrypt C1 in these positions instead, now it's an OR gate. And so we can do AND, we can do OR, whatever gate we like, and so we can do any kind of computation that we want. Cool, so as an example, so that was a single gate. The other little piece of this puzzle is we need to be able to connect these gates together. So yeah, so just, me as the garbler, I will just connect the output of an AND gate to the input of some other gate. And so you can build up something like this or any Boolean circuit that you have compiled using summon or any other method if you want to use another method. And so if I want you to calculate this on my behalf, I will just tell you what are these kind of like arbitrary values that correspond to the correct values on those input wires. And then, so what will happen is that in these two gates, you will find that you can decrypt E0 and F1. So on wire E, you'll have E0, but again, you won't know that it corresponds to 0 because it's a random number. And so that allows you to get these numbers. That allows you to decrypt this row over here. And so then you'll get G1 out, and you can send that to me, and I can know, the answer to my circuit is 1. And I didn't do the calculation, you did the calculation, even though you can't see. So again, I think like at the moment, this is just like a really inefficient way of doing computation, right? But it illustrates the point of the kind of the magic of you're calculating something, even though you're not looking at it, which is something that we need to do when we do MPC. How's everybody doing? Are we tracking? Yeah?
A quick question. So the goblet provides the encryption ciphertext.
Correct.
But to compute all the combination of the correct ciphertext, it does need to do all the computation, right? For example, for an OR gate, it has A0, B0. It has to come up with E0.
Yeah.
Like the, beforehand, and then prepare the encryption, like
Sure.
for E0. So basically, the goblet does more computation than.
Oh yes. It's a lot. It's very inefficient.
Right.
Like, yeah, it's interesting actually if you think about the philosophy of it, right? Like when I prepared this AND gate, I guess I kind of did an AND operation to know that in this entry I should put a 1 here, and on the other entries I put a 0. So I evaluated 0 and 0, 0 and 1, 1 and 0, and 1 and 1.
Yeah. So basically, it prepared all the possibility of all kinds.
Yeah. But because we break it down gate by gate, you don't have the like combinatorial explosion of like all possible inputs and all possible outputs, which you could also do. You could accomplish MPC by just doing a full table in like one big inefficient gate. Yeah, obviously we do it this way. And so the kind of the real magic, I guess, is more like you're able to link these operations together in the correct way, because like I may have done, if you think about calculating something more interesting, which is like, you know, how do I get from here to Wollongong? You boil that down to AND gates, but you know, when I prepare that circuit and I did, you know, billions of AND gates and billions of OR gates, and like the full complement of all of those, you wouldn't consider that I had ran that computation. It's really you who did the computation, even though you can't see it.
Yeah, and so my kind of, well, this is pre-computed, like a pre-processing, right?
Yeah.
The circuit. The computational power you need for the pre-computation is actually higher than the evaluation, because the other end evaluator would just decrypt.
Yes, there is more.
But then you, the
computation.
goblet, should do all the encryption.
The goblet does more computation than the evaluator, yes.
Okay.
Yeah.
But like you can kind of, if you knew the topology of your circuit, you can just pre-process, keep many graphic circuits in memory. So
Yeah, there's actually a bunch, like, so it's not implemented in MPC framework, but one of the like big optimizations that you can do if you're going to do lots of MPC interactions with the same counterparty is you can do a lot of like pre-work, like before you know what the inputs are to the function, and then you can run the function relatively much faster, because most of the work is work that you can do ahead of time, even before you know what the inputs are.
Just one other thing, we got 10 minutes left, because I'm not too sure whether we have other meeting later.
This room
Yeah.
is not used
Oh.
until 1 o'clock.
Cool, I didn't realize I was going that long. All right, cool, I think I can wrap it up in that amount of time. Okay, so to make this actually interesting, the point is like I want you to be able to specify some of these inputs rather than me specifying some of these inputs. So then neither of us knows what's going on. Like even though I didn't do the calculation, I could have easily done the calculation myself. But if somehow you can provide the input, some of the inputs, without sharing them with me, then you'll be able to do the calculation and we'll get an output that neither of us kind of know fully what's going on. So somehow I want you to provide those two values. So I can provide A1 and D1 as normal. And so, but now we have this little sub-problem, which is that, you know, you get to select, if we just focus on this wire, because, you know, it's the same problem as this wire. Focus on this wire, you know, if you want your bit to be 0, then you need to get B0. If you want your bit to be 1, then you need to get B1. but somehow you need to learn only the one that you're supposed to have, and not the other one. But I'm not allowed to know which one that you got. So it's actually like another MPC problem, but we can't solve it with recursion. We need a different kind of solution to this. Because there's two like obvious solutions to this problem which don't work. One is like I could provide you with both B0 and B1, but then you would be able to like test both of your values and then choose the output that you wanted, which is not acceptable. The other solution is that you could tell me what your bit is, and then I could tell you the corresponding wire. But the whole point is I'm not supposed to know your inputs, so that's not acceptable either. So, these slides just kind of explain that if you had both of these, you could decrypt both of these rows, and then you could decrypt all of the rows of the outputs, and then you could choose whatever you like, and that's not okay. So yeah, I have B0, B1, you have your little b, you know which one that you want, and you need big B sub little b only. So we can represent this as a diagram like this. This is called oblivious transfer. So I will provide those values and learn nothing. You provide this thing and you only get this. So the way we do this is a very interesting modification of Diffie-Hellman key exchange. There are other ways to do this actually, by the way, but the most common is this one that's built on top of Diffie-Hellman key exchange. So I'll recap that briefly. So Diffie-Hellman key exchange, similar idea, but we just provide like arbitrary numbers in, and then we get a common shared secret out based on those values. Cool. So this depends on like, finite field arithmetic, but the algebra works. I imagine you guys might be familiar with finite fields. And maybe Diffie-Hellman key exchange as well. So, but anyway, so it just, it looks like this. You both just raise your generator to the power of your random number, and then you can just swap it, raise it again, and then you get the shared secret because of the commutativity of the multiplication and the exponential laws and stuff like that. But yeah, once you have the shared secret, then I can send a message to you encrypted with that secret, and even if somebody was spying on these communications, they wouldn't be able to see the message that was exchanged. Cool. So the solution that we use is called Chu-Orlandi oblivious transfer, which is our twist. And what we do is we say we still want to get a shared secret out, and actually we're going to get the same shared secret that we would have gotten if we were doing Diffie-Hellman key exchange. So we introduce these new arbitrary numbers x and y, same as if we were doing Diffie-Hellman key exchange. And we're going to land on the same shared secret actually that we would have previously. But what we do is a twist. So you get to do a twist as the person who's choosing which wire label you're going to get, B0 or B1. You will either do this twist or not. So instead of sending me g to the power y, if you apply the twist, you multiply by g to the power x. And so then on my side, what I'll do is I will ordinarily just like raise this to the power x again, but I will also untwist by dividing by d to the power x to come up with the alternative secret. And so what's happened here is like, if you did the twist, then secret 1 will be the valid secret. And if you didn't do the twist, then secret 0 will be the valid secret. Either way, it's the same thing that you would have had in Diffie-Hellman key exchange. And the point is that the other secret is just invalid. It's impossible for you to know what it is. And so from that point, all I do is I would just encrypt both of the things that you might need to know using those two shared secrets. And remember, only one of them is valid. And then you'll get the one that you chose. You'll only be able to decrypt successfully the one that you chose, and the other one will just kind of look like random noise as far as you're concerned. And so that's how we solve that piece of the puzzle. And so we use oblivious transfer so that you get those wire labels that you need and nothing else. And then you can evaluate this circuit, same as you did before. And then you can give me the answer, and we've achieved MPC. And so so overall, we can represent this protocol like this, where I provide x, you can provide y, and we both get out f of x and y, which is pretty cool. And so, but there is a little bit of a problem. So I mentioned authenticated garbling before and the semi-honest problem. So if you think through this carefully, when I was constructing the gates, there was no way for you to know, like I was supposed to be doing an AND gate in our exam, but there's no way for you to know that an AND gate is actually what I encrypted. So I could have encrypted any gate that I liked in that slot, which effectively means that I get to choose what the circuit is, and I could have calculated g of x and y instead of f of x and y, and that, for example, might just reveal your input or some kind of masking over your input so that I get to learn what that is instead of calculating the correct thing. Or maybe even you could get away with calculating the correct thing and also leaking your input. That would be really bad. So good solution to that is authenticated garbling, but there's a lot more complexity that goes into that, which I don't have time to cover. Okay, so quickly, I kind of have two parts. So there's this other thing called jumbo swap, which is less intimidating than like comparing salaries. So if you want to try MPC, you can try jumbo swap. I have these little like charms, so you can take one to use for this demo. So the idea is you like swapping with people in a group. So you can do more than 2 people, by the way, as well. So that's also something that I haven't covered. You can do more than 2 people, still secure, still cryptographic assurance of the correct output and all of that stuff. So you might imagine like if you want to swap things, you don't actually really want to express that you want, someone else's thing, right? Because then that person will be like, oh, well, my thing is valuable, and you don't want your thing, so why would I give it to you, right? So this allows you to get all of your intentions, like they can just be inside of the MPC, calculate swaps that are compatible, and then you get the swaps out and you can solve that problem, and also not leak that maybe you are interested in other items unless you actually get to have them. So similar to the ballpark app before, post and join, specify your name, thing you're swapping for, and specify the things you're interested in swapping, calculate.
Is this some sort of multi-hop atomic swap or something?
Well, what do you mean?
Like for atomic swap, for example, what you typically do is like between 2 persons you want to have this fair exchange, right? And here you want to have multiple people to do the exchange. Is that
Yeah. So I mean it only kind of reveals the information about what swaps would satisfy the things that you're willing to do. And so in this version, you actually just kind of swap those items in meat space. So you have to agree that, we're actually going to go ahead with these swaps, which probably you'll be willing to do because it corresponds with your intentions and you have to participate in the swap in order to get the thing that you're interested in getting. But it is possible to link this to blockchain and do a swap that way and make it atomic.
it's some sort of generic multi-hop atomic swap, right?
Yeah, I think I'm not quite getting the terminology that you're using. Multi-hop, like. Oh, because it's not just one-to-one.
Yeah,
right?
exactly.
Like
Because you want to have some intermediaries to treat for the stuff that you are not necessarily want, but in order to confirm the final pass for the entire swap, you have multi-party, therefore multi-hop.
Yes. Okay. Yeah. I think that it does make sense. Yeah, that is a good way to describe it.
Yeah, I have a quick question. This exchange ensure fairness. I mean, you have cake, I have a cookie. If I give my cookie to you, is it ensure I must give the cake back from you?
Kind of. So the MPC application is only calculating that this is what you should do.
Yeah, there's no enforcement.
There's no way to enforce, this app doesn't enforce that because it's like a physical item that you then have to I can't write code to move this item.
Let's say if there are some digital objects.
Yeah.
You have a secret, I have a secret. If I link my secret to you, can I get your secret back?
Yeah, that's right. So you can do stuff like that. Yes, it is possible to do that sort of thing, yeah.
Is it supported by your framework or?
I have not written code specifically for it, but you could.
This is a private order book.
I mean, There is an impossibility resulting that you cannot do fair exchange without any trusted third party, right? How can you do that here?
Oh, yeah, so.
That's why I got this a bit of the confusion here.
Right. Okay, no, that's a good point. So, okay, the digital solution that I have in mind is linking this to blockchain. So technically, I guess you're leaning on the blockchain consensus in order to solve that problem. So
I
in
see.
theory, like it's not a perfect solution. It's like not a perfect atomic swap, but you need to you need to manipulate the like Ethereum consensus or whatever, which will cost billions of dollars in order to do it. So it's just like it's not going to happen.
Sure.
Yeah.
I have a simple question. So in your this multi-party swapping example, is it literally 3 people running the computation at one time, or is still doing pairwise computation using 2 PC before?
No, it's a special thing where like everybody participates together. It's not like multiple rounds of 2 PC.
So it's really 3 PC, right? Then the gobble circuit won't work. You need to change the protocol.
Right. Yeah. I mean, it is different the way that it works. So there's like, in addition to the authenticated garbling stuff, there is also kind of a way to generalize this to end parties, which is like, not covered by what I was talking about before. Yeah. But it is still boils down to Boolean circuit and garbage gates and that sort of thing.
So is there any ePrint or anything about this workflow?
Is there what? Sorry.
ePrint, like any
ePrint.
any documented algorithms.
Oh, that's a good point. Yeah. The so garbled records. I've had this linked to me before. Send me an email. I'll get you. That's a good question. Oversight. This one, I think. Yeah. Cool. I think it's linked on if you go, there'll be a QR code for the MPC framework website later, and you'll be able to find it in there. But also send me an email if you. Oh yeah, so very quickly, I don't have any slides to cover this, but if you're interested in working at the Ethereum Foundation, this is a link to the jobs page, and there are a bunch of different positions, and there's also like a completely open-ended application as well. So if you want to do that, feel free, and maybe we can have a chat as well if you like, and I can maybe forward some information about you that can go with your application if you're interested in that kind of thing. And yeah, that's pretty much it. Thank you so much.